Welcome to tonight's lecture, which is part of the Hyde Lecture Series, hosted by the College of Architecture. I have the pleasure of introducing tonight's speaker, Kent Duffy. And before I introduce Kent, I want to remind you that we'll have a brief question and answer session immediately following the lecture, so please stick around for that as well. And for those of you who are hoping to scan your in-card and get credit for attending the lecture, we'll have that available on your way out as well. You can look towards the back, raise your hand. Yep, in the red sweatshirt. She has the device to scan your in-card. Kent Duffy holds a Bachelor of Architecture from the University of Oregon, as well as a Master of Architecture and Urban Design from Harvard's Graduate School of Design. His experience within the profession includes 9 years with Moshe Safdie and Associates, as well as 28 years with SRG Partnership, where he served as a design principal. During his time at SRG, Kent collaborated with the Energy Studies and Buildings Lab at the University of Oregon, led by G.Z. Brown and our very own Kevin Vanden Wijmelenberg. Kent's talk this evening will center around the topic of design values and their presence in both the design process and lived experience of architecture. Please join me in welcoming Kent Duffy.
Thank you for the introduction, but I'm honored to be here. And I really appreciate being invited. I'd like to talk about some things which are actually close to my heart tonight. And one of them is design education. And the reason I bring that up is that design is a very personal act. And what I realize is that you're asking yourself, each time you make a design decision, you are trying to figure out what's the right decision, and it's all coming out of your own values. What it is that you hold dear is what's at the root of how you make those decisions. And I've come to think of design training, in essence, as intensely asking yourself over and over as you make decisions. That was a good idea. You know. What is it that I hold dear in this moment for this thing I'm trying to decide? What is it that I would use to make that decision, or what things? And that actually, those are really thought-provoking questions. Sometimes profound, sometimes really very present in your mind, sometimes hidden in the problem you're trying to solve. How can I make this work even better? I would say that for the most part, it happens very gradually to you. You learn what it is you value by going through the exercise over and over and making those choices. And so it emerges kind of slowly, and you don't realize exactly what's happening. But there are things that happen that your values can change over time as you go through your career. But there are certain things you hang on to that really mean something to you, and you go back to over and over. And at least I feel like I'm getting some kind of feedback, so I'll wander to the other side of the universe over here. And what happens in my experience is that, sure, it's a gradual process, but also some really, in a sense, dramatic things can happen that change the way you look at things. And I'm going to tell you about two in particular that happened to me, and they happened in my final year at the University of Oregon, only a few weeks apart. And the first was a studio of one of my professors. I had several professors who studied with and worked with Lou Kahn, and I confess that I'm a fan of Lou Kahn's work from way back. And I apologize, Kevin, you've probably heard some of these stories before. But I had a chance to take a studio based on the program for Kahn's Unitarian Church in Rochester, New York, but I was given a choice of 2 sites in Eugene, Oregon. And so there was, it was a different place. But also my professor, Pat Piccioni, made a big deal out of the fact that there were two equal things in the program. One was the sanctuary and one was the fellowship hall. And he made an even bigger thing of saying we had to take those two equal things and express unity with them. Now, I have to say that this was the only time in my whole career that I kept finding a fatal flaw in my approach and starting over and over and over. And finally, 3 weeks before the final review, I hit on a scheme that stacked these two equal things and united them with light wells that fed them both. And poured myself into it. Night before the final review, Pat Piccioni walks in the room and starts going desk to desk to see how people are doing in preparation for the final. And when he got to my desk, he said, "Tell me about your scheme." And I told him, and he said, "I think you have a problem." And I said, "What is that?" And he said, "They aren't equal. The upper one has more light in it than the lower one. So you're not meeting the goal of two equal things. You may have united them, but they're not equal." And in classic form, I tried to explain to him how that wasn't true. They were in fact equal, and the light was going to be great. And he said, "Actually, no, it's not the same." And so I said, "Well, what should I do?" And he said, "I think you should start over." Just talking about it's hard. I had never imagined the possibility of failing a design studio. I was a good student, but I thought it was inconceivable that I could be in this position. But I dove into it. I started sketching and coming up with things. And in that classic way, you've been there for several days already. And so I worked till about 3 in the morning. I found 2 or 3 fresh approaches, and I found a fatal flaw in those 2. And but I had a structures exam at 7:30. So I went home and got a couple hours of sleep, took a shower, got some breakfast, and took the exam, and then went back in the studio and frantically trying to find a scheme in the next couple hours before the review starts. And about an hour and a half before the review, I got an idea about a single object that if I made 2 of them, they interlocked to make one thing. They didn't exactly replicate the program, but it was 2 equal things that made one thing. And I made a tiny corrugated cardboard model of that. And for the review, I put up my 6 schemes I had rejected and a stool with this tiny cardboard model sitting on it. And I had the best review of my entire career. Didn't expect to get so excited about this, but the dean was on my review committee. And I held him in very high regard. I had never had him on a review committee before, but there I was, so just do it, So I explained my schemes, why I had rejected them, and when I got done, the dean walked up to me and said it was clear there was only a matter of time until you had an exceptional scheme. And going from thinking I was crashing and burning to getting a compliment like that was an incredible turn of events for me. The personal lesson I learned was that it was more important to have a scheme worth carrying out than it was to have a scheme done on time. And that's a lesson that I have used throughout my career. Make sure you've got a scheme worth carrying out. don't just meet the deadline, meet the goals. So I managed to recover from that. Spring break came, and I met up with some friends of mine in Southern California to look at architecture by famous and prominent architects. I mean, Frank Lloyd Wright, Green and Green, Schindler, Neutra. It was a fabulous trip. And I can't emphasize enough, get out and see the work of architects that you admire. Maybe some you don't even know about yet, but you discover what a good job they did in their projects. So I'm seeing most of these houses, they were almost all houses, in fact they were all houses, and they were intimately scaled, fabulously detailed, the incredibly expressive use of materials and sighting. And I was in the car with my friends. They had the car, they were deciding where we were going, and they announced that the next day we were going to go see the Salk Institute by Lou Kahn. And I was both excited and scared because I had never seen a Kahn building in person, and I'd been looking at these fabulously detailed, intimate buildings, and now I'm going to look at an institutionally scaled building, and I don't want to be disappointed in Kahn's work. So the next day we're driving down there, and we arrive in this gravel parking lot, and I thought, where is it? And then it was just a grove of trees, and you can't see anything through this grove of trees. You start meandering through it, and you start to see just the outline of the kind of image of something beyond the trees. Now, some of my professors worked on this project, and they told the story of Jonas Salk asking Kahn to make a place for people with very diverse points of view and ideas and backgrounds to come and find a place that they feel both welcome in and to share their ideas and to make a place that can explore fresh possibilities. And when I emerged from those trees, I emerged at one end of a courtyard that is framed by two laboratory buildings, two series of studio spaces for the scientists, a fabulous paved courtyard, travertine courtyard with a fountain that's 2 sheets of water folding into a single trough of water going the length of the courtyard. And I just was stunned. And I didn't, it was completely unexpected that I would have such a strong response to the building. I walked over to the concrete walls, and I don't know if anybody here is familiar with the building, but there are ridges where the form boards met in the concrete because they beveled the edge. And what I perceived, and somebody's going to probably chuckle, but I perceived love radiating from the walls where those ridges were. And as I walked to the stairs, towers in the studios, concrete walls, concrete stairs, but where your foot would touch them was a piece of travertine laying there, just for you to step on. If you look at the studio towers, they are open on the ground floor, enclosed studio space, an outdoor seminar space, and then another studio space above that. So they were making a place for people to come out of their studios and into an open air discussion place where they could talk to somebody in the next group and come on over and let's join our discussion. And it was just, everywhere I looked, I couldn't imagine it being any different. And then as I looked at it, I realized I feel like this building is a personal gift made for me. It's presented to me as an individual person. And I knew it wasn't true. They didn't know who I was. But it was an absolutely fabulously feeling to feel profoundly cared about. And that became, from that moment forward, what was operating in my own design process, making places where people feel deeply cared about. And the premise is simple. If I made places good enough, then the people who occupy them could have a comparable experience to what I had, so that whatever they did, they would try to pass on that level of caring in their own profession, whether they were a teacher or a scientist or a librarian or whatever. Whoever was occupying that building would want to treat the people around them with their expertise in a similar way. Now, so now you know where I'm coming from, and some of the students met with me earlier today, and that's what was in my mind. I was trying to help them find a way to make places that the people who came there felt profoundly cared about. Now, when I meet with students, I often ask them 3 questions. I didn't do it today because I didn't want to steal from my own lecture, but there are 3 questions that I often put before students. And the first one is, what do you value? And the second one is, what do you want to be part of? And the third one is, how will you contribute to it? Now, you probably would like to see some slides of some kind, so I've got some. And I collaborated for 20 years with researchers at the University of Oregon, and it was the Energy Studies and Buildings Laboratory, and we worked really hard to make buildings energy efficient and good to be in many ways. If you'll go to the next one, actually just go ahead. So at the beginning, the first thing we worked on was the business school at the University of Oregon. And if you look really carefully, I mean, you can see there's a lot of glass here, but you can also see some lines in the glass. I'll come back to those in a few moments. But the next image will show you that it was actually a new building, 140,000 square feet, 4 stories high, connecting to 3 buildings and setting it up for a 4th building in the future. It kind of had a pivotal point in the campus. There was a north-south axis going through the whole campus that passed through the building. And so next slide. So we got deep into the design process, started in 1999, and in 2000, LEED emerged on the universe, and they said, could we make this building a LEED certified building? And in the spirit of trying to figure out what that meant, they suggested we talk to the Energy Studies and Buildings Lab that Kevin and Charlie Brown were leading. And so we talked about all kinds of things, and one of them that came up right away was if we had more thermal mass in this building, we could use it to passively make the building comfortable. And but we were deep into a steel building, and we didn't have as much thermal mass as we were supposed to. So the possibility of having to convert from steel to concrete arose. We already knew that was going to cost more, but we explored it. But we also asked ESBL to tell us how much more mass we needed. And they said, after about a week, they came back and said, you need 2 more inches of thickness in the floor slabs in the building, and you'll have all the thermal mass you need. Now, what that meant was we could have the performance of the building, save $1 million, and things could work better in the building. And that was, at least for me, that was a breakthrough, so that we could have a chance to do that. Next slide, please. And it's just, we were focused on a strong daylighting scheme. You'll see in the next slide that even the lecture halls those are not lights over the back of that lecture hall. Those are skylights with operable louvers. And when you walk in the room is dark. You hit what you think is a light switch, and it opens the louvers and lets the daylight in. And but we also, at the same time, didn't wash out the chance to project video images on the front of the classroom. We had separate lighting for the presenter, separate lighting for the chalkboards. So we really tuned these spaces to work well and have daylight in them. Next slide. But the basic building block of much of the program was a case study room. You can see clear story windows at the back. And you'll see the ceiling is sloping slightly to help angle the light. But if you go to the next slide, these are what's called the daylight factor, and it's just a percentage of the light available in the sky that's in the room. We were shooting to make sure all the students could take notes by daylight while they're also using video projection on this surface down here with no conflict. And we made it work in all those case study rooms without any problems. Next slide shows you a kind of, everybody will look at me cross-eyed when I talk about this, but we realized that if we had the thermal mass in those rooms, if we added ceiling fans to help people feel comfortable when we need to cool the spaces for their comfort, we could actually come very close to making the building passively cooled. So what we did was, so the thermal mass is in the floor and in the ceiling fans are stirring the air in the room. We also had a vent here at the back that brought air in under the raised tiers and brought it out in the room. And the punchline is we could make people comfortable the vast majority of the time. And the university said, that's nice, we want a cooling system. So we provided a cooling system, but the next slide shows you that that cooling system was required to be in use for 4 hours in the entire calendar year, all of them after 5 o'clock. And for me, that was, wow. All this time I've been, turning to my mechanical engineer saying, what do you need? How are you going to make the building comfortable? I didn't realize what a role I had in shaping them having the starting point for that question. And for them to realize that they had a different environment to work with than just a raw, my fans and my cooling units will solve this problem. So, anyway, so that's for the Lillis Business Complex. I learned that working with researchers could really pay off in my practice. Next slide. So again, these are those same photovoltaic cells that are there, partially for shading, but partially for generating electricity. But it just also creates an architectural character at the same time, which is very pleasant. Next slide. So we got hired shortly after that to do an academic building at a seminary at a monastery in Oregon. And if you go to the next slide, this is Mount Angel Abbey, and the building right up here is a library by Alvar Aalto that is, at least in Oregon, revered. And it's a fabulous space. The building way at the top corner above that, actually go to the next slide, is the building we did. And I want you, the first thing you notice is there's a lot of stuff on the roof. So you can see each classroom has its own skylight in this low front bar. You can see right behind the skylight is a row of turbine ventilators. And then you can see two small circles next, kind of adjacent to those skylights. Those are the inlets and outlets for a heat recovery ventilation system. That means that you're going to bring in fresh air from the outside. In the summer, it pre-cools what's coming in the winter it preheats what's coming in to minimize the heat, what the mechanical system has to do. So, next slide. So a lot of it is a one-story building. All the classrooms are on one level here, and then this is 3 stories right here, and it's primarily offices and meeting rooms. You can see that there's actually quite a variety of the sizes of classrooms. And take note of this one, you're going to see it later. It's the one where you learn to give a homily. So it's essentially an octagonal room that has a different character. So next slide. You can see here, so there's the section, so that's the classrooms, here's the stack of offices. What's interesting is that if you're trying to do natural ventilation, you have to control, in a multi-story building, it's a big deal to not short circuit between floors. So you have to find a way to isolate the airflow through the building so that the floors operate independently. In our cases, on the left, on the classroom side, every classroom was independent. It was, if it was in use, it was operating at the level and had CO2 sensors, and it operated the systems based on how many people were in the room. If it was unoccupied, it went down to idle mode and waited for people to come in again. And so next slide. So this is the entry side. Next slide. This is the office side with sunshades because it's facing south. We had a in-the-floor heating system in the public spaces. This is a bench, and I'm sorry, we thought of this corridor as part of a cloister. I don't know if you're familiar with monasteries, but they often have a courtyard with a perimeter walkway with benches, and it's a contemplative place to go and sit and have a conversation with somebody. We treated this corridor as a portion of a cloister, so so often we have a bench under a skylight with a mosaic art piece on the wall and the densest pattern of the heating coils underneath it. So if you sit down on this bench with somebody to have a conversation, you're in a pool of light with great art and the warmth of the building encouraging you to sit there and have that conversation. The next slide. So here's the pattern, the basic idea behind the classrooms. Light comes into the skylight, which has louvers in it. The light comes down and bounces off of a reflector, bounces off of a sloping ceiling, and the light is distributed evenly throughout the entire room. And air is brought in high and low through this space to be in contact with the thermal mass. And it goes out, comes in one side and goes out the other side. No fans are involved. It's just air pressure differentials that draw the air up into the building. If there happens to be a breeze, it spins that turbine on the top, and that encourages the airflow, but basically it's free cooling. This building has no active cooling system and is comfortable year-round. Now, if you go to the next slide, here's what it looks like in this typical rectangular and square classrooms. What we got was criteria. Criteria make it open in the middle, make it more reflective around that, then less reflective, and then letting more light come through at the perimeter so that we could balance the daylight. If you go to the next slide, this is that octagonal room for the learning to give a homily, where we did a round version. And I want to make sure you know there's no electric lights on in this photograph. This is all daylight balanced within the room. And the next slide shows you in detail, we had to get a custom extrusion made for this triangular section. But the punchline is, it does a phenomenal job. The top surface of the triangle you see, the flat one facing that's horizontal, that's doing all the work at balancing the light in the room. But every other shape we tried, and we tried a lot of them, the reflector looked like a dark cloud under the skylight in contrast. And so we had to find a way to minimize the surface that was in silhouette, and basically said a triangle has no bottom. Great, that'll do a great job of meeting that need. Now, next, this is where it all began. This is an artificial sky chamber in the lab. Next slide shows you what the model looked like that we studied to get to these decisions. That's the outside of it. The next one is the inside. And so it's really, in a way, it's really crude, but it is asking the basic questions. What happens if you try this? Next slide. So then we looked at criteria, and we had all these different people thought different amounts of light should be in a classroom. But we went not for something precise, we went for a range. 20 to 45 foot candles was our goal. We figured that you could have that much fluctuation and people wouldn't be alarmed by it, and you wouldn't always hear buzzing of louvers opening and closing and doing things. Next slide. So here's the deal. That same model you just saw, if we put just one, so this is the section, if we had that much opening, there was a skylight in the center of the room, the results, we were shooting for a daylight factor of 4 because we were trying to make it work even in the winter when there was light at the beginning and the end of the day was dim. We had way too much light. We had heat gain, we had glare, we had contrast ratio. That was no good. So the next slide shows you that we tried, okay, we'll try some louvers. And that basically cut the light level in half, but we still had glare and heat gain and contrast ratio issues. And then we tried, next slide, just a reflector. Now that kind of wasn't too bad, but still had too much contrast ratio in it. But the next slide shows you what happens if you use both of them, which is what we have in that room. And it just evens it out, so it's essentially imperceptible. Now the next slide shows you when there's enough light in the sky to get 20-foot candles in that room, at least 20-foot candles. And if you would go to the next slide, this overlays when the building was in use. And it tells you that 95% of the time the building's in use, the classrooms require no electric lighting. That also means we don't have a heat gain from those lights. So that contributes to making the cooling system, the passive cooling approach, viable. Next slide. So I didn't count them, but the next project shows you that we learned that we could rebalance how much thermal mass we had in the building and how much turbine ventilators we needed. We cut the number of turbine ventilators in half by having slightly more mass in the classrooms. So this is a building for Lane Community College, also in Eugene. The next slide shows you, actually go back for a second. This is, all of this is student housing, and all of that up there is academic. And if you go to the next slide, we explored over 20 versions of how to configure this building on that site. The one we chose is the next slide, which is the yellow L is the student housing. This is the academic building. It's entered here. The housing is actually entered over there. They share a common courtyard. The next slide shows you that we found ways to get the daylight in on a 4-story building. The next slide, as we had a heat recovery, ground source heat pump underground. We actually had parts of the floor that were glass panels to see the pumps underneath the floor. Next slide. And we found ways to thread the air through that building, all 4 stories, distinctly, so we didn't undermine our own efforts to get the air to move smoothly. Next slide. And the courtyard was here, and in the center of the courtyard was a conference center that also was skylit and ventilated. And next slide. So over the entrance, we were working, they had an energy management program that was going to be one of the occupants of the building. And they wanted something like on Lillis, where we had the photovoltaic cells in the facade, they wanted some dramatic statement. And they said, where's our equivalent of that? And at that point, we didn't have one. But then we installed this. I'm just going to reach up higher. That is an evacuated tube solar thermal system that supplies 70% of the hot water for the 255 beds of student housing, at the same time as cutting the heat load on the south-facing facade of the building. And it's denser up at top than it is down below, because there's a screen to allow you to look out and see the city around you, because it's a downtown campus. So here is that transition between the densest part up there and the not as dense part here. But it balances the light, it balances the heat gain, and it makes a lot of hot water. Next slide. So if we go to the evening, we had a chance for Portland State University's School of Architecture to renovate a 1915 elementary school into their home. And can't remember if, so I talked to somebody about pivoting panels. Are you here today now? Okay, back there, okay, watch closely. Next slide shows you that we used, again, the only money in this project, it was a state budget funded by a study that was only for seismic retrofit and mechanical upgrade. So we didn't have any architecture budget in the whole building. But we can make decisions that would cut down on how much we had to spend on the mechanical system so what we did was we put in we had some shear walls in the building, but we needed more. We just made those walls thicker and stronger. That also added thermal mass to the building. It was a concrete building, so it had thermal mass to start with. And then we took some of the money we saved and we made spaces. This is a kind of combined conference and library space amongst the faculty offices in the building. This is a big steel and glass door that we made, and the point I was making earlier today was the glass doesn't weigh as much as the steel, but if you find the right pivot point, you can balance that and make that an easy door to open. Next slide. They also asked us to demonstrate the act of making in the building. So back here you see some metal panels up above. Those metal panels slowly transform across the room from flat to three-dimensional. So you can see that the next slide shows that we actually etched a line and a direction of what should happen at that point. And slowly, and the panels all had all those commands on them, but as they got across the room, the next slide shows they came fully three-dimensional on that side of the room. So we were just trying to work with their aspirations for how they were teaching architecture and engaging students with materials and things. But the next slide, this was the big deal. We made the studio space comfortable for the first time in the first 100 and more years it was there, because it was always too hot in the summer and too cold in the winter because it had an inadequate heating system. But we installed a radiant panel system in the ceiling, and it also is used to reflect light. It also houses the ceiling fans that push the air down, like I've talked about before. And in one space, next slide, in a student lounge, we turned the panels upside down so they could see what was making them work. And it was, anyway, they liked it. So, next slide. And one more bit about this. So, in a library for a community college, we actually, the next slide, we actually had a situation where we had a skylight at the top, and a lot of not clear story, but lots of windows, and we had too much light on the top of the library, and we didn't have enough light in the middle level, and as so often happens, the reflectors to get the light increased to the lower level or middle level were cut out of the budget. They were an additive alternate that wasn't taken. But we made a pitch to the owner during construction and explained to them that we would be able to minimize the amount of the excess of light on the top floor and double the light on the middle level if we put these reflectors in. And in fact, if you go to the next slide, they look like that. If you look up into them, they're also spaced so that we can have air moving through them for, as air is moving by static pressure. Next slide, you see what it's like on the top. And what it actually does is kind of break up the space, and so you have a series of elements within it that you can find your place to work with your friends to on a project. And the next slide is what it looks like underneath. And anyway, so if you have researchers like we had to work with who can spell out criteria and means, you can do a lot of amazing things. I'm going to go to the next slide because, and go straight to the next one. So we got hired to do a project for a mass timber parking structure as a demonstration project to show what you could do with mass timber. And the trick was they wanted it all to be on display. Don't hide anything. They wanted it to be something which generated people thinking freshly about how to approach mass timber projects. So this is a 200,000 square foot parking structure. It's net positive for water, net positive for energy. And it's, the thing is, we managed to make a different layout. There's a pedestrian walkway around the entire thing, which helps shelter the wood structure. But if you go to the next slide, you can see a stairway at the end, and then go one more slide. Actually, we'll go back. So no, stick with this. So this is that walkway. So all the parking spaces are on essentially level. There's nobody's parking on a ramp. Your stroller's not taking off down the ramp. Your whatever. And the idea was that we could use that to shelter all the wood structure except the bottom half of the columns. What we're going to do with the bottom half of the columns, because Energy Studies and Buildings Lab found out for us when it rains, how hard the wind is blowing and which direction. And we could use that information to place very specific pieces. And it's hard to see in this slide. Go back one. So right here, these guys, those vertical stripes, are a stainless steel spiral fabric that actually hangs at a strategic location to keep from having the wind blow the rain onto the bottom half of the columns, because we weren't getting the extra points for demonstrating that wood could rot if it gets wet. And I was suspicious. We actually tested this fabric. We didn't really believe them, but when the rain hits it, it's deflected by it, but some of it clings to it, and it all goes down through those spirals and dumps out of the bottom of the building. It's an amazing thing to see it in action. So next, let me just say, we also had the chance, this upper right-hand corner, these are called post tensions rocking CLT, or cross-laminated timber shear walls that have been in development and been testing. But in an earthquake, they rock back and forth, and when the earthquake is over, the post-tensioning cables snap them back into their original position. And a 4-story version of this has been tested with is an increased version of the Northridge earthquake. I think 120% of the Northridge earthquake. They did it, they stopped, they did it again, and there was no damage whatsoever. The building, most buildings you have to repair after an earthquake. This was ready to go after the earthquake. So if you're ever working someplace where you're worried about earthquake damage, you need to think about this kind of structure as a real tool. And again, partially because it's wood, it flexes, but it also snaps back into place and is ready to go again. And we would have never known about this if we hadn't been working with people who want to research these kinds of things and get deep into making buildings perform. So now you're entering the final moments of me talking. One more, next slide. So at the University of Oregon, we did that business school, and Charlie and company got a grant to do research about microbial communities in buildings. And they realized we had inadvertently set up a perfect experiment in the Lillis Business Complex. So the deal is, I mean, we are surrounded by microbes. Every one of you and everyone in the world sheds 1 million microbes every hour. So we are immersed in the world of microbes. The question was, what's this building like inside? If we do a lot of natural ventilation in this building, does it affect that? If we do a lot of daylighting in this building, does it affect that? Next slide. So they tested 300 locations in the building. Next slide. They mapped how people move through the building and how connected they are. So the same person sheds some of their microbes here and some there and some over there. So you get this kind of overall sense of distribution of microbes by doing these swab testing. Next slide. So here you can see this is a gradation of what kind of community it is. If it's more based on what's outside in nature on this side, it's more based in people on that side. So you can see on different floors there were similar spaces that were quite different. Next slide. So the natural experiment was, there was a huge debate when we were designing this building between faculty about whether or not they wanted offices to be naturally ventilated and cooled or mechanically ventilated and cooled. And it split 50-50, and we made 50-50. So this side here is mechanically ventilated, and the blue side there is naturally ventilated and passively cooled. So, well, I didn't see it coming, frankly, but it makes sense in retrospect. If you go to the next slide, the blue oval up there is showing you kind of what the microbial community in the naturally ventilated office is like. And the one down here is kind of red or maroon kind of color, is what it's like in the mechanically ventilated spaces and cooled spaces. And they overlap because there are people in both spaces. But the one that's blue is more like what's in nature outside, and one down here is dominated by what people have brought into the room. And pardon me, Kevin, I'm going to overreach, but the punchline is the mechanical system was doing a fabulous job with all the outside air it was taking in, all the natural community air pouring into the building from the mechanical system, had filters in it, and it's doing its very best job to get all of those microbes out of the system and pump air through that doesn't have them. Which is great, except what it means is that the microbes that show up in there are from people. People who cough or sneeze or don't wash their hands or carry something which has something else on it and move around. So in a way, the mechanical system that tried to be so high performance and clean, in the end has a flaw in it. And so if you could actually make a building use more natural ventilation, there's more chance of it being a healthier environment. Now that's an overreach. I'm sure Kevin would say there's 15 other studies need to be done to declare that, but the punchline is there's a difference. And you can decide for yourself what it is you're going to use as your criteria. I haven't got anything else to say, so if you've got questions, I'd be happy to make an attempt to answer them.
Thank you, Kent. That was wonderful. We do have time for a few questions from the audience.
I'm curious how you came up with the idea for using natural wind from the outside as ventilation for an interior of a building.
I'm sorry, the question is, how did we come up with the idea of using natural ventilation?
Yes, for the natural ventilation.
It's at least in the world I'm in, people are hungry for it. They want natural ventilation. They're tired of being stuck in buildings that they can't open a window. The trick is getting the right combination of windows to open at the right, or openings to open up at the right times. Most of the time that we're naturally ventilating the building, it's overnight, where we flush the building with what we call a night flush. We cool the mass, and we get it all, and then we cinch the building down and close all those things up during the daytime when it's heating up, and try and just use the thermal mass. It's like if this floor is cool enough, it can, rather than heat radiating from my body to heat this room up, that heat will be drawn to the cooler surface. Many of you have had high school physics or physical science or something. You know that heat gravitates from a warm surface to, from something warm goes to something cool to try and warm up the cool thing. That's what's at work. If you just have it at the right times, then you do well. And I have to say, I would go to the lab, the research lab, before I interviewed for a building. I would try to scheme out how to talk to the client about it before I even applied for the chance to design a project. And it was a real tool for me to have their input into my earliest thinking about how to approach the basic building. That answer your question? Thank you.
Other questions? I should have just stayed back there.
I see you did the microbiome study. Have you been able to do any other studies on different viruses and the transmission of that after COVID-19, and how the different circulation systems affect the different levels of cleanliness in different rooms based on how the air is circulated?
Well, that study was done before COVID. It was a curiosity question. It was done 6 years after the building opened in 2003, but there have been a bunch of studies done relative to COVID and the spread of COVID vaccines, germs, not vaccines, but viruses. Since then, and actually Kevin is the one who led the majority of those, or all of them. Am I right?
Yeah, I'll answer really quick because we used some of Ken's buildings to do the work. And I'll just say that this study played out, but with different microbes, those being the virus. And the mechanically ventilated spaces had more abundant natural ventilation, or excuse me, the naturally ventilated spaces had more abundant airflow than the mechanically ventilated spaces. And basically the solution to pollution is dilution in that case. And so the naturally ventilated spaces performed very, very well with regards to degrading and eroding the signal of virus in the space.
I'm not sure if this is going to be a question or not, but I think one of the things I was really struck by in the introduction, talking about your experience as a student with the Charettes and then the Louis Kahn building, the experience of the Salk Institute and having the realization that it was some kind of individual gift to you, seeing the profound meaning in that building, and then transitioning into these slides where you're studying architecture in a very technical way, looking at systems, and oftentimes, students are introduced to those two things. I think they often find trouble in synthesizing them, of putting together the kind of meaningful poetics of architecture on the one hand with the scientific, technical study of architecture on the other. And I'm curious if you could talk about how you see that synthesis within your own career.
Well, let me first of all say that I am the son of a contractor, so I grew up around buildings. I grew up with a thirst for how buildings are put together. You know, what the sequence of construction is, how do you think things through in advance to make the process of actually building a building successful. And but I also my time in school was a time when essentially stripped down modernism was modernism where you couldn't afford to do anything that just looked good. You had everything had to work. Everything about the way the building was built had to add up to the character of the building. And so I was constantly trying to find some way to make an expressive building with the least possible means, but it meant I had to pour my heart into how the building was made. And I think that was just a rich introduction to making buildings that don't have additional layers of materials added to them. It's just making the essential things wonderful. And it's part of my nature. I'm not alone in people from that time period, but it's always stayed with me. Does that answer your question? Yeah. I'm sorry, go ahead. Are there other questions? Because I have one thing I want to say before we're all done. But
All right, we'll take one more question and then.
Do you believe that the change in wind speeds due to climate change could potentially impact the way that you use wind to ventilate your buildings?
what was the last part? Say it again.
Do you think that the change in wind speeds due to climate change could potentially impact the way that you use wind in your buildings?
The thing I worry about the most is that climate change will be more extreme than we've been able to anticipate so far. I don't, it's a good question. I guess when I listened to your question, I was thinking wind speeds. Are wind speeds increasing or decreasing? Is that going to make the buildings more or less effective? We counted on pressure differential with no wind to make the air move through the building with no fan power. So in a way, any wind power, any wind on top of that, making the turbine spin, actually makes it more efficient. But I mean, the Mount Angel building with no active cooling system went through a week of high temperatures of 106 and 107 degrees, which are way outside the norm in our world, and it stayed comfortable for a week. And so I think there's a certain amount of grace tucked into what we've done, that it'll be okay. But the truth is, I don't know. You know, that's my intuition, but I don't know if it makes a difference or not. So my turn. One more slide. So, you know, you're all being trained as individuals. You're being trained sometimes in teams to be architects. But both here at school and in the profession, it absolutely, the way you treat the people around you matters. And I can't say it too strongly. I mean, the simple thing is, somebody asks you a question that makes you think about something profoundly. Thank them. If somebody else contributes an idea to what you're doing, tell them how much you appreciate it. When you're working, you know, to some extent you think you're maybe competing with the people around you, but the truth is you need everybody taking care of each other, doing a good job of appreciating what each of you are offering in order to be successful. You know, I mean, part of what my story is today is how much I appreciate working with those researchers who made it possible. If I didn't have them, I would have been guessing or using intuition. I wouldn't have any idea. And I can absolutely tell you that mechanical engineers, when I was doing those buildings, were fighting me. They were leading revival meetings to shout down all the measures in those buildings that made them energy efficient. And you just had to find a way to get through it. And so treat the people around you with both respect and appreciation and admiration, and tell them, don't just think they know, take care of each other. It's going to make every one of you more successful.
Please join me in thanking Kent Duffy one more time.